Hey guys, let's talk about Coulomb's law. And let's start with the comparison of Newton's law of gravitation with Coulomb's law. So Newton's law of gravitation described the force between two masses. So if you have two masses, m1 and m2, then the force between them is given by this formula, g m1 m2 over r squared, where g is the gravitational constant. So the physical picture looks like this. You have m1 here, m2 here, separated by some r. Then to find the force between them, you would use this formula. That would give you the magnitude of the force. And the direction of the force is always attractive between two masses. Okay, for the case of electrical force, it's given by Coulomb's law. Okay, Coulomb's law of force says that force between Q1 and Q2 is K, Q1, Q2 over R squared. Okay, where Q's are the charges and R is the separation between the charges. So suppose you have Q1 here and Q2 here, and they're separated by some distance R. Then you're gonna find the magnitude of the force between Q1 and Q2 using this formula, and the direction of the force between electrical charges can be either attractive or repulsive. So in this case, both charges are positive, so they're going to repel each other, and the direction of the force is going to be along the line that joins these two charges. Okay, so suppose you had a positive Q1 and a negative Q2 separated by some R. Then, same thing, you're going to use Coulomb's force law to find the magnitude of the force between them, and the direction of the force is going to be attractive. If you have two negative charges, okay, then they're gonna repel each other. Okay, so electrical force can be either repulsive or attractive. Gravitational force is always attractive. Okay, one other difference is that electrical force is much stronger in magnitude compared to gravitational force, given practical considerations. So suppose that you had a positive Q here and another Q here, identical charges separated by 1 meter. Okay, suppose the magnitude of Q is 1 Coulomb and this one is also 1 Coulomb. Okay, then the force is going to equal K times Q1, Q2, which becomes Q squared divided by 1 meter squared. So a remark, K is equal to 1 over 4 pi E naught, okay, which is equal to 1 over 4 pi times 8.85 times 10 to the minus 12, and that's equal to 9 times 10 to the 9 Newton meters squared per Coulomb squared. Okay, and charge is measured in coulombs, and 1 Coulomb, and the charge on an electron is equal to 1.6 times 10 to the minus 19 Coulomb. Okay, is the charge on one electron. Okay, so 1 Coulomb is equal to the charge on 6 times 10 to the 18 electrons. Okay, so the force between these Q's in this case is going to equal 9 times 10 to the 9 newtons. Okay, so now what if you had two masses, m, and another mass m here, separated by a distance of 1 meter? Again, we're talking about point charges and point masses here. Then the force between them is given by g m squared divided by 1 squared. Okay, and say we want to know how much masses we have to have in order for the force between them to be the same as the force between 1 Coulomb of charge. Okay, then we want the force to be 9 times 10 to the 9 and equal to G times m squared. Okay, 1 doesn't matter in the denominator. And G is 6.67 times 10 to the minus 11 times mass squared. So that implies that mass is about square root of 10 to the 20. So it's about 10 to the 10 kilograms. Okay, so you need billions of kilograms separated by 1 meter to have the force of 9 times 10 to the 9 newtons. Okay, that's not very practical. On the other hand, 1 Coulomb of charge is not hard to come by. Okay, you can have, you see very often capacitors that can hold 1 Coulomb of charge. So because the force of charges is so much stronger than the gravitational force, it makes a lot of electrical devices feasible, like batteries and capacitors, that you cannot have with the gravitational forces. So now let's do a problem that is slightly harder. So suppose you have a charge Q and another charge minus Q separated by a distance r, and you have another charge, say plus Q prime down here, and you have to find the net force on Q prime. Okay, so in this case, to solve this problem, we're going to use the principle of superposition. Okay, the principle of superposition says that when you're finding the force on a particular charge, Q prime in this case, okay, you can find the force between Q prime and some other charge, okay, let's say negative Q, while forgetting about all the other charges involved. Okay, so we're going to find the force between Q prime and negative Q and forget about the plus Q, and then we're going to find the force between Q prime and plus Q, forget about this negative Q, and then add those forces vectorially. Okay, so let's first talk about the direction. What is the direction of the force between Q prime and minus Q? The direction of the force is going to be attractive along the line that joins them in this direction. Okay, and what about the direction of the force between the Q and the plus Q prime? Okay, so this is the line that joins them. So it's going to be repulsive in this direction. Okay, so let's say you're given this side is, let's say this side is R prime. Okay, then you can find this angle. Okay, what would this angle be? So this side is R over 2 from here to here. So then this angle is called theta, is going to be inverse tangent of R prime over R over 2. Okay, so then this angle is going to be the same as this angle, right? Because this line and this line are parallel, and these are alternate interior angles. Okay, so now we have the angle and the direction of the forces. Now what about the components, the direction of the components? Okay, the direction of the components of this force, the x component is going to be here, and the y component is going to be here. Okay, and the direction of the components for this force, the x component is here, and the y component is here. And this angle is also theta, right? Okay, so to find the net force, we need to find the sum of forces in the x direction on Q prime, and the sum of forces in y direction on Q prime, Okay, so what are the forces in the y direction? So the magnitude, okay, so the force between q prime and negative q is going to be k q prime over this side. So now what is this side going to be? Let's call this r, and this is going to be r over 2 squared plus r prime squared. Right, so this, it becomes r squared. Okay, r squared times what? Times sine theta, because we want the y component. Okay, and so what about this force? The y component is going to be pointing downwards, minus k q prime over r squared. Again, it's sine theta equal to 0. So see, the y component ends up equaling to 0, and could we have foreseen that before? We could have, right? Because look, this component is pointing upwards, this component is pointing downwards, and these forces are equal, therefore it had to cancel. So we didn't even have to calculate the y component of force. You could have just said beforehand that the y component of the forces is going to be 0. Okay, because they're equal and opposite, so they cancel each other. What about the x component? So x component for q prime and q is going to be k q prime over r squared cosine theta. Okay, and then q prime and plus q is going to be, it's pointing in the same direction, so it's going to be plus k q prime over r squared. So that would be the force on q prime in the x direction. Okay, so notice that we didn't care about the sign of the charges. We figured out the direction of the vectors first, and then, depending on where the vectors are pointing, we decided on our signs. So that's why both this component and this component are pointing in the same direction, are having the same sign. Okay, so you found the net force on q prime. So if you place a q prime at this point, it would feel a force in this direction. And suppose you knew the mass of q prime, suppose it has mass m, and you were asked to find the acceleration of q prime, then you would set this equal to ma. Okay, I hope this is clear. So now let's do another problem. So suppose you have a charge q1 here, or a q1, so suppose you have a charge q1 here and a charge q2 here, a distance r, and then also at a distance r you have a charge q3 and you have a charge q4 that's negative. And say you need to find the force on q3, the net force on q3. Okay, so now we know how to solve this kind of problem because we've done this problem just now. Okay, so we need to find the forces on q3 in the x direction. We need to find the forces on q3 in the y direction. And that's how we're going to find the net force on q3. Okay, so again we're going to use the principle of superposition. So first you find the force between, let's say, q3 and q2. The direction of the force is going to be repulsive, so q3 is going to be repelled by Q2 here. So this is the direction of force between Q2 and Q3. Okay. What about the direction of force between Q1 and Q3? This is a line that connects Q1 and Q3. So this force is going to be in this direction. So this is the force between Q1 and Q3. Okay, and Q3 is going to be attracted by Q4. So the force between Q3 and Q4 is going to be in this direction. Okay, so we're going to need to break force between Q1 and Q3 into components. So the components of this force are going to be this x component and this y component. Okay, and what about this angle? What is this angle over here? Since this is a square, it's going to be 45, right? So this theta is equal to 45 degrees. So here, let's just call it theta. So then, what are the forces? Okay, so now that we know all the forces in the x direction, all the forces in the y direction, geometrically, how are we going to, how are we going to translate that into the equations? So, in the x direction, we have the force between Q1 and Q3. The x component of that force is going to be K times Q1 times Q3 divided by, okay, we need this distance. What is this distance? It's square root of 2 times r. Right? Because this side is r, this side is r. When you do Pythagorean, you're going to get square root of 2 times r. So square root of 2 times r squared times cosine theta, which is 45. And then the force between the other component that's in the x direction is the force between Q3 and Q4, and it's pointing in the opposite direction, so it's going to be a minus sign here, minus K Q3 Q4 over r squared. So this is the force in the x direction. Okay, and then the force in the y direction on Q3 is going to be the y component of the force between Q1 and Q3, which is going to be K Q1 Q3 over square root of 2 r squared sine theta, and the force between Q2 and Q3, which is also going in the same direction, so it's going to be plus K Q2 Q3 over r squared, and that's it. That would, this gives you the x and y components of the force on Q3. And let's say, okay, and then define, if you wanted to find the magnitude of the force on Q3, so that would be the x component that we found plus the y component that we found, square root, Pythagorean, right? And then the direction of this force would be, you can find the angle by doing inverse tangent, the force on Q3 in the y direction divided by force on Q3 in the x direction. Okay, I hope you followed this. So let's do another example. So say that you have a charge that's hanging from a string, a charge of Q, say plus Q, and another charge of plus Q here. and this, suppose this angle is theta, and this angle is also theta. Okay, and then suppose you're given this distance r, and suppose you know that gravity is pointing downwards, and this system is in equilibrium, so neither q's are moving. So then say you need to find the tension in the cord. Okay, so how would we go about doing that? So first of all, okay, so we know that these q's are not moving, so that means the system is in equilibrium and the acceleration is 0. Okay, so we're gonna have, you know, the forces on q in the x direction, and we're gonna have forces on q in the y direction, and they're gonna be something, and they're gonna, when we set them equal to ma, since a is 0, this becomes 0. Okay, and same thing in the y direction. Since acceleration in the y direction is 0, it's going to be 0. Okay, so what are the forces in the x and y directions? So we know that there's going to be the electrical force. So let's do some of the forces on this charge. Okay, so this charge is going to be repelled by this q due to the electric force. Okay, it's going to be attracted by gravity. So suppose it has some mass m, and suppose that was given as part of the problem. I forgot to mention it. And suppose this is also m. But let's ignore the gravitational effect between these two masses. Okay, suppose they're suppose these two charges are very small for the gravitational effect to be significant. Okay, so mg is going to point down, and then there's going to be tension. Okay, so the rope is going to be pulling this charge in that direction. So then in the x direction you have electrical force, which is k q squared over r squared, and that's going to be countered by tension, so minus t times what? Times sine theta. Right, and that's equal to 0 because these are the only two forces in the x direction. In the y direction you would have mg minus t cosine theta equal to 0. Okay, so cosine because that's the adjacent, that will give you the adjacent side, and that's the vertical component of t that we need in this problem. Okay, so t, the components are like this. The y component of t is here, the x component of t is here. So that's what's happening in this problem. So, okay, so so now, you know, it becomes an algebraic problem. You have two equations, and at most you can have two unknowns. Okay, so one of the nice tricks about, you know, that you can use in this problem is this. You know, take this to the other side, kq over r squared equals t sine theta, and then mg equals t cosine theta, and then divide both equations. You end up getting kq over mg times r squared equals tangent theta. Okay, so what we did was we took this side and divided it by mg, took this side divided by this, so tensions cancelled, then sine theta over cosine theta becomes tangent theta. Okay, so then this is going to give you theta, and then once you know your theta, you can plug it into, you know, plug it back somewhere and find out your t. Okay, so you have to, you know, they can only ask you for, this problem can only have two unknowns because you only can have two equations. So as a final remark on Coulomb's law, you're going to encounter three kind of problems with Coulomb law. One is going to be discrete distribution of charges, like the first two problems that we worked out together. where we used superposition to find the sum of forces on a particular charge. And then there are going to be miscellaneous problems like that tension problem. You might have a charge moving in a circle where you might have to use centripetal acceleration to figure something out, given the force between the charge that's moving, and there can be like a nucleus in the middle composed of so many positive charges. And the third class of problems that you're going to encounter are integration problems. So in these problems, you have to, like it sounds, you have to integrate over the given distribution of charge to find the force on a particular charge. Okay, we're going to cover these in later videos. Next video is going to be about electric fields. See you then.